Welcome to Rules of Differentiation. Let's just jump right in. The derivative of a constant function is 0. And this reads d by dx of c. That means take the derivative of c, and it's equal to 0. So the derivative of, over here, 4 is 0. Now geometrically, y equals 4 is a horizontal line. The derivative is the slope of the tangent. For a line, the tangent is the actual line, so that we see the slope everywhere here is 0. Okay, the power rule. The derivative of x to the n. Bring the n down and then subtract 1 from the exponent. So over here, for example, the derivative of x to the 5th, bring a 5 down and subtract 1 from the exponent. Now, e to the kx has its own special derivative formula. We bring the k down and we do not subtract 1 from the exponent. We leave it alone. So, for example, over here, the derivative of e to the 2x is 2 e to the 2x. All right, we're going to do a bunch more examples till you get this. The derivative of x, so this reads d by dx of x. Think of x as x to the 1. I use the power rule. I brought the 1 down, and then I get x to the 1 minus 1, which is x to the 0. So the derivative of x is 1. Now geometrically, y equals x is a straight line, and the slope is 1. So the derivative is 1. Okay, next one, d by dx of x squared is 2x. Geometrically, x squared is a parabola. We see we have 0 derivative at the origin because there's a horizontal tangent, and that's this point here on the derivative. And then positive slopes when x is positive, so this line goes up, and then negative slopes when x is negative, and that's over here. Okay, now I'm changing up the notation. X cubed prime, that means take the derivative of x cubed. So that's 3x squared by the power rule. Okay, next one, we can't use the power rule right away. We have to write this 1 over x as x to the n. So I haven't taken the derivative yet, so I need to write the derivative sign. Just like limits, if you have to simplify before you take the limit, you carry along the limit sign. So this is d by dx of x to the negative 1, which is negative x to the negative 2. Bring the negative down, subtract 1 from the exponent. And if I want to write that with positive exponents, that's simply negative 1 over x squared. Okay, next one, we also have to do the same thing. We have to simplify before we can take the derivative. This is d by dx of x to the 2/3. If I write that as a fractional exponent. Drop the d by dx because we're taking the derivative. Bring the 2/3 down. X to the negative 1/3. And if I wanted to write that with positive exponents, I'd put the 2 on top, and the 3x to the 1/3 goes on the bottom. All right, constant multiples. Constants can come out of derivatives. So for example, if you want the derivative of 2x to the 5th, you can just carry along the 2 and multiply by the derivative of x to the 5th, which is 5x to the 4th. Now in reality, you're going to do that step in your head. You're going to bring the 5 down. 5 times 2 is 10, and then subtract 1 from the exponent. Okay, sums and differences, the derivative of a sum or difference is just the sum or difference of the derivatives. So for example, the derivative of 3x squared minus 5x is 6x minus 5, because the derivative of x is 1, 5 times 1 is 5. All right, and here are the notations for higher order derivatives. You can keep doing primes till you get to 3, and then you use the number like 4, but you put parentheses around it to indicate it's not an exponent, it's a derivative. And these are Leibniz notation examples. All right, so some more examples. Find the first 3 derivatives of y. Y is a polynomial. So first derivative, we bring the 3 down. 3 times 2 is 6. X squared plus 2x. And the derivative of 5 is 0. Y double prime is 12x plus 2. And finally, y triple prime is 12, and that's it, because the derivative of 2 is 0. After that, all the derivatives will be 0. Okay, another problem where we have to simplify. So when you take the derivative of y, in this example, you cannot take the derivative of the top and divide by the derivative of the bottom. We need to simplify this. So I'm writing y equals, not y prime. So y is 5x over x to the 1/2. We practiced simplifying things like this in the first week, and this is why we did it. 2x cubed over x to the 1/2. And then this is 5x to the 1/2, subtract exponents, minus 2x to the 2.5, which is 5/2. Okay, and now we take the derivative. So now I write y prime equals. I don't want to keep writing equals because now I'm changing from y to y prime. And I get 5/2 x to the negative 1/2, using the power rule, minus 5x to the 3/2. And there's my derivative. Okay, next one. Again, in order to take the derivative here, first we need to simplify so we can use the power rule. So y is equal to x to the 3/2 minus 3x to the 1/2. Now I take the derivative. Y prime is 3/2, bring the 3/2 down, x to the 1/2, subtract 1 from the exponent, minus 3/2 x to the negative 1/2. Now sometimes we'll want to write our answer with positive exponents, and this is one of those times. So that's equal to 3/2 x to the 1/2 minus 3 goes on top, 2x to the 1/2 goes on the bottom. And we'll take the derivative of this using the product rule on the next page, and we'll see we get the same answer. Okay, last one before we do the product rule. Why is this polynomial? Find the slope-intercept form of the tangent line at x equal 2. So the first thing we need is the slope. Then we need a point on the graph. So y prime is the slope of the tangent. Y prime of x is 6x minus 6. So the slope, m, is y prime at 2. And I want you to use this notation. So y prime of x is a function, y prime of 2 is a number. Put 2 in for x, and we get 6. So now we know the slope of the tangent, and we need an x naught, y naught, which is the point on the graph. Now we're told x is 2, and so to get the y value, we need y of 2. All right, and you can see that that's 2, 7. If you pause the video, make sure you can verify that. And so now we use point slope. Y minus y naught, which is 7, is 6 times x minus 2. And this implies, if we want to write that in slope-intercept form, y is 6x, and that would be minus 5. Okay, part 2, find the x-coordinate where the tangent is horizontal. All right, so horizontal tangents have slope 0, so we want to set y prime of x equal to 0 and solve for x. So y prime is 6x minus 6. We set that equal to 0. This implies x is 1. Okay, product rule and quotient rule. The derivative of f times g is f prime g plus fg prime. And I strongly suggest you use the order I have it written here. Of course, you could change the order because addition is commutative, but it's helpful to do f prime g first, because then when you talk about the quotient rule, the numerator of the quotient rule is identical to the product rule, except it's got a minus in it. It's f prime g minus fg prime over g squared. And those are two rules that you certainly need to memorize. There's just no way around it. So here we've got a function that is the product of two other functions. So root x is my f, x minus 3 is my g. We did this problem a different way on the previous page. Now we can find y prime using the product rule. So we take f prime, which is 1/2 x to the negative 1/2, multiply by g, and then add on x to the 1/2 times the derivative of g, which is 1. Now let's distribute to see if we get the same answer that we got on the previous page. This is 1/2 x to the 1/2 minus 3/2 x to the negative 1/2 plus x to the 1/2. And if I combine like terms, I get 3/2 x to the 1/2 minus 3/2 x to the negative 1/2. And that is indeed what we got on the previous page. Okay, here's another one. Now I want to find the derivative of a quotient. So the red is my f and the blue is my g in the rule above. So h prime of x is going to be a big fraction. And on top, I want f prime g, which is 2. F prime is 2. G is 3x plus 4. And then I subtract f, which is 2x minus 1, times g prime, which is 3. And that's all over 3x plus 4 quantity squared. All right, let's clean that up. On top, we get 6x plus 8 minus, if I distribute the 3, I get 6x plus 3, because there's a minus minus. And then I'm going to leave the denominator factored. Usually we do in the quotient rule. And then that simplifies to 11 over 3x plus 4 quantity squared. And that's my derivative. Okay, one more. Find the derivative of h. This is a product again. This is my f, and the e to the 2x is my g. So h prime of x is, we want f prime, which is 5, times g, which is e to the 2x, plus f, which is 5x, times g prime. Remember, e to the kx has its own special rule. We bring the 2 down, and we leave the e to the 2x alone. And so if I simplify, that's 5e to the 2x plus 10x e to the 2x. And finally, I'll leave you with a caution. Don't use the product and quotient rules when you don't need to. You can, but you're likely to make a mistake. So for example, constant multiples don't need the product rule. The derivative of 5e to the 2x is simply 5 times the derivative of e to the 2x, which is 2e to the 2x. So that's 10e to the 2x. And the next one, d by dx of x squared over 7, it looks like a quotient, but really it's just d by dx of a constant, 1/7, times x squared. So the 1/7 just carries along. When we take the derivative, I drop the d by dx. That's 2/7 x. All right, and I've got some proofs on the next page. And then that is the end of this section.